In this paper, we investigate the use of multimodal large language models for generating virtual activities. Given a virtual environment as the input, our method leverages multimodal large language models to automatically generate contextually realistic character interactions. The output is a sequence of scene snapshots captured at distinct keyframes. A core part of this work is enabling vision language models to understand virtual 3D scenes using combined visual and linguistic information. We feed multi-view scene images to the multimodal large language model, which helps them recognize scene objects, their functionalities, and affordances. We additionally group scene objects into distinct clusters called scene areas, considering distances and visibilities as additional inputs. We propose a prompting technique called layout chain of thought to guide multimodal large language models in reasoning the area's adjacencies and using them as edges to complete the scene graph. Specifically, layout chain of thought involves guiding the model through a sequence of reasoning steps. Areas adjacencies could be reasoned if one view contains objects from multiple areas, or reasoned from multiple views. For instance, while each of the two views by different camera poses focuses on a distinct small area of the scene, the shared object suggests the proximity between these areas. Using the interpreted environmental context, we then prompt the model to generate dynamic, context-aware virtual activities, comprising a series of scene snapshots taken at discrete keyframes. We define a structured format that leverages multimodal large language models' capabilities in interpreting and generating complex scenarios, instructing the model to fill out the fields. We further designed a 3D pose optimizer that takes into account the generated textual activities and the scene semantics, considering the characters' positions and rotations to place their 3D poses in the scene accurately. We showcase 3D animations of generated activities within indoor environments of different types and scales. Inside an apartment, a family consisting of a father, mother, son, and daughter shares a moment. The family gathers around the table to share dinner together. After dinner, the two kids head to the bedroom to play with their toys. The mother takes a quick nap and heads back to the living room. Meanwhile, the father relaxes for a moment, then begins tidying the tea table. With the night settling in, the parents relax in the living room. The son has gone to bed, and the daughter freshens up in the bathroom. A restaurant is full of diners. Staff move around to serve, and chefs check in with guests for feedback. While the staff stay busy attending to tables, some diners wrap up, pay their bill, and exit the scene. At the office, staff are busy at their desks. Some employees chat in the lounge areas. The CEO and CFO meet privately in the office. Employees move around the office, engaging in discussions with colleagues at desks and in shared spaces. Later, the CFO hosts a meeting in the conference room. Additionally, we validate the applicability of our approach to AR scenarios by testing it on real-world 3D scans. The results of real-world scenes highlight lifelike activities and demonstrate our method's potential for generating realistic human scene interactions in practical AR applications, utilizing 3D scene scans to serve as AR digital twins. We conducted a perceptual study to evaluate the quality of virtual activities generated by our method compared to manual professional designs. We invited 5 technical artists to create virtual activities in 5 different small virtual scenes. They were asked to include some virtual characters, create their activities, adjust their poses, and select proper animation clips to match the context they wanted. For each manual design, we used our method to generate contextually similar virtual activities for fair comparison. We recruited 100 participants for this study. Following a two-alternative forced choice format, they watched paired video recordings and chose a better one regarding each of the 4 evaluation metrics. The selection rates for ours were generally close to 50%, indicating similar preferences to designer results. A chi-square test confirmed that the differences were not statistically significant, supporting the conclusion that our method produces results of comparable perceptual quality to human-designed content. Meanwhile, our method takes noticeably less time compared to human-designed processes. This is the end of the video. Thank you for watching.